Hi, everybody. I'm Greg Fishel. Welcome to another bonus video about radar. And we're going to talk about a couple of the limitations of radar today. One is something called attenuation, and the other one relates to the curvature of the Earth. And so we'll talk about both of those. So let's start off with the curvature of the Earth issue. And so I'll move my cursor up here. And I'll move my little trusty radar maybe up like that. Maybe let's turn it around like that to account for the curvature of the Earth. Okay, so what I'm going to do now is hopefully, I want to make sure I'm picking the right tool here. Oh, there it is. Okay, so I'm going to imagine, and I'm of course a terrible artist here, but I'm going to imagine that this is the surface of the Earth. Gosh, that's awful. All right, and then this is our trusty little raindrop up here. And we'll move that up like, maybe like this, okay? Now, the radar signal is tilted up at about a half a degree elevation. And the reason for that is that not all of the radar's energy goes out in a straight line. There are what we call side lobes. And those side lobes bump into the ground, and the radar is not smart enough to know the difference between a raindrop and mud and grass and concrete. And so it shows up as a return. So the radar pulse, if you will, or the beam, is tilted up just slightly to minimize that effect. It doesn't eliminate it, but it at least minimizes it to some degree. And there are all sorts of algorithms that have been developed now. Like, for instance, if you're getting a consistent echo from something and it's not moving, then that probably means that it is associated with the Earth. And if the Earth starts to move, then we have a whole other problem. But basically, a lot of techniques have been developed to try to cancel out the ground clutter, and so you can just see what's actually going on from a weather standpoint. But the bigger contributor to the problem is the fact that the Earth is round and the surface is curved. So let me draw try to draw an arrow here. And so now remember, the radar doesn't transmit in a continuous beam, but for the purposes of this argument, I'm going to make it look like that. So the signal goes out like this, okay? And the raindrop is, at some elevation above the Earth's surface. If the raindrop was over here, let me pick the right cursor here. If the raindrop was over here, the same distance above the Earth's surface, the radar would have no trouble detecting it, okay? But because it's the same distance over here and the Earth surface is curving away like that, then the radar beam goes right over top of it and it never sees it. And so this is the reason why it's important to have a network of weather radars that are spaced in such a way so that it minimizes the chance of something like this happening. Like, for instance, if the National Weather Service radar in Raleigh was looking at a thunderstorm over Wilmington, okay? Now, if that thunderstorm is 60,000 feet high, it's still going to pick it up, okay? But let's say it's just a shallow shower that's only about 8,000 feet high. That thing's going to go right over top of it, but the National Weather Service radar in Wilmington will have no problem seeing that at all because it's much, much closer to that raindrop. So that's one thing that you need to be careful about. The other thing has to do with what is called attenuation. So I'm going to move this trusty little raindrop over here like this, and I'm going to create a second one, and it's going to be out about like this, okay? Okay, so let's draw our arrow again, and I'm going to do my best to draw it through both of those raindrops, okay? And let me get back to my cursor. There we go. All right. So there are different wavelengths of radar signals, okay? and they're usually described by a letter. So there's an X band, which is a very, very short wavelength and is only usually good at very, very short ranges. Then there's a C-band radar, and that has a wavelength of 5 centimeters. And then you have an S-band radar, which the National Weather Service uses, and that is a 10 centimeter wavelength. So this is just a simple matter of physics, okay? That when a 5 centimeter radar signal, or pulse, if you will, is sent out, then a lot of that energy is going to get absorbed by this first raindrop, okay? And very little of it is going to be able to poke through this raindrop to see the other one on the other side. And TV stations have 5 centimeter radars. And I will never forget, and this actually happened many times, that there was a strong thunderstorm near Roanoke Rapids up in Halifax County. And there were other thunderstorms that were between our radar and Roanoke Rapids. It was picking up those pretty well. But the storm over Roanoke Rapids looked pathetically weak. When I looked at it using the National Weather Service radar, which is only about a mile away from the WRAL weather radar, it showed that Roanoke Rapids thunderstorm as being much, much, much more intense. And so I had to make a decision at that point, which one was I going to show? Well, it wasn't a very difficult choice. You show the National Weather Service radar because you want the folks in Roanoke Rapids to realize that this storm is intense and threatens them with perhaps damaging winds, large hail, tornadoes, or whatever. You don't want to show your radar just for promotional purposes if it isn't accurately depicting the weather, okay? So I never looked at our radar as being in competition with the National Weather Service radar because it couldn't compete, okay? The National Weather Service radar has more power. It has less attenuation issues. In other words, it can poke through one storm and see what's on the other side. The dish that actually transmits that pulse is twice the size of the dish that TV station radars use. And so it's not a contest. And in the next video, I will go into one of the advantages that I thought that a television station radar had that has now almost completely gone away. Basically, the National Weather Service radar is the Cadillac of weather radars, okay? And anything else but that is going to fall very, very, very short. And that's okay, you know. But the nice thing about these, television station radars is sometimes they could fill in gaps. Like, for instance, Charlotte is the biggest city in North Carolina, but of the major cities, it is the one in our state that is farthest away from a National Weather Service Doppler radar. The closest one is in Greenville, Spartanburg. So TV stations in the Charlotte area that have their own radar provide a real service because they can see precipitation particles that are close to Charlotte and that the radar 50 miles away is not going to be able to see as well, okay? But in the case of Raleigh, the WRAL weather radar, the WTVD weather radar, and the National Weather Service radar are all within 2 miles of each other, okay? So you're not filling in any holes, okay? They're all seeing the same thing, and the National Weather Service radar is seeing things at a distance better because the signal does not attenuate as much as a 5 centimeter radar does, which is what the TV stations have. Okay, probably rambled on a little bit more than I needed to about that, but that is the bonus weather video talking about radar limitations. And I will, in the next video, talk about, again, a situation where I thought the TV station radar had a distinct advantage during severe weather, but that advantage has more or less vanished. That's coming up on the next video. Okay, you all have a wonderful rest of your day, evening, whenever you're watching this, and we'll talk to you soon. See you later.